Now we will see the context of this presentation. Deep learning systems are ubiquitous. Everyone knows now that since 2012 there is a huge scientific and industrial revival on the use of deep learning systems. It mainly comes from the fact that we have lots of computing resources, from GPUs, big data platform that allows to store all the training data, and of course the end of manual extraction of characteristics. This aspect allows non-experts of the data to be able to use machine learning because they do not have to know how to extract things of interest. There are numerous applications and use cases of deep learning systems. They can be used for segmentation, instance segmentation, classification, clustering, dimension reduction, data generation, and so on. And it is almost data agnostic because deep learning system can be used with many tensors. We can store tabular data, images, videos, sounds with tensors. They can also use graphs, structures, business data, text, and so on. However, there are several challenges to solve for deep learning system. First, they are sensitive to data bias and attacks in operational environments. So they can generalize poorly in operational systems and having bad performances. They can be easily attacked, so we can trick them. We also need to have masses of data to train them, and the amount of data needed to train new models can be too huge for research labs. It cannot offer. We will not be interested to these 2 points during the presentation. We will be interesting to the next one that considers the black box effect. Models are often too deep and complicated to understand exactly what they do, or which part of the network do what exactly. There are also several regulatory limitations that forbid the use of automated decisions without explaining them. And as deep learning systems are black boxes by instructions, they do not explain what and their acceptance can be difficult in some use cases, and their decisions can be criticized. We can think about usage in health, safety, or autonomous vehicles. Explainability is one solution to this black box issue. Usually, with standard machine learning system, we use standard evaluation metrics or graphics that provide information about the performance of the system, and thanks to that, we are able to know if they perform well or not. But it does not bring more information. Explainable artificial intelligence goes beyond that and tries to help to understand the reasons of this performance. Explainable deep learning is explainable artificial intelligence that focus only on deep learning specificities. And the work that interests us has been tackled by various communities with different approaches. Deep learning community, explainable artificial intelligence community, and visual analytics community. So this work will contribute to various aspects. We have several objectives and several kind of persons to target. So our first objective was to collect and organize the design choices of visual analytic systems, the explanations that are used inside them, and how they are connected. We have analyzed the papers and the applications, extracted their common characteristics, what are the common foundations, and also the limitations. And the aim is to try to bridge the communities to which this article is directed. So what are these communities? They correspond to the researchers and practitioners in these 3 areas: deep learning, explainable artificial intelligence, and visual analytics. We have analyzed several works from the literature. We were interested by visual analytics solutions that are trying to explain deep neural network. So initially we have collected almost 200 papers, but among them we have collected only 67 because the others do not correspond exactly to our criteria. Each paper has been categorized using 38 dimensions, and those dimensions are explained in the paper. Of course, there are already similar works in the literature, and our difference are the following one. We focus on deep learning and not machine learning in general, and we focus only on explainability and not broader aspects. Now I will give you some information about the background that will serve to understand the rest of the presentation. So there are different aspects that are involved in deep learning systems and that can differ among them. First, we'll consider the architecture of a deep neural network. The smallest component is a neuron. A neuron generates some kind of number that is named activation, and how this activation is computed? It is computed by doing a weighted sum of its input, and eventually applying an activation function on it. What is a network? A network is just the computational graph of the. So we have a graph where neurons are connected to neurons of previous layers. So this computational graph can be abstracted as an architecture graph where a layer is represented by a block and there is an arrow between two successive depending on the kind of connection inside these layers, we obtain different families of architecture, and these families depend on the tasks to solve and the input data. We have the convolutional neural networks, recurrent neural networks, transformers, autonomous neural networks, and other kinds of architecture that can be observed in the literature. Different data can be used to generate the explanations, and here we are listing them. Can see that there are the input samples, their ground truth, the prediction of the deep neural network, activations maps and attention maps that are generated inside the network, evaluation metrics, loss function when we are training the network, gradient when we are training the network. So now we'll see at which different steps this data can be used. So during the inference, we need to feed a network with one or several input samples, and it will generate some predictions, and eventually activation maps and attention maps. So the different data can be used explanation. During the training, we have more information because we fed the network with the input samples to obtain the prediction, but as we also have the ground truth, we are able to compute a loss. So thanks to this loss, we can also compute the gradients that will be used during the gradient descent to update the weight of the deep neural network. During the evaluation, it's quite similar to the training. We feed the network with input samples, we obtain the prediction, and this time instead of computing the loss by comparing the prediction to the ground truth, we compute other kind of metrics that serves for the evaluation. So that's all for the data that can be used.
The field of explainable deep learning aims to propose methods to understand deep neural networks. They usually propose answer to questions like why the network is returning a specific prediction, what the networks learn during the training process, and how they work. These explanation methods and explanation returned by these methods can be used by visual analytics solutions in order to help users to achieve their goals. For example, in this slide you can see an example of an explanation. There is a deep neural network that classified an husky as a wolf, and the explanation is telling us which part of the image are considered important by the network in order to be classified as a wolf. And in this case is the snow in the background and the nose of the dog. We analyzed the literature of visual analytics solutions that employ explanation methods to help users understanding deep neural network, and we identified 5 micro categories that group methods that share the same goals or similar explanation objects. These categories are feature attribution, learned features, explanation by examples, counterfactuals, and model behavior. For each of these categories in the next slide, we will see the explanation methods or the explanation object used to provide explanations, and a couple of examples of how visual analytics solutions can use these methods to help users to achieve their goals. The fifth category is feature attribution, where these methods aims to associate a score to each features of the input, telling us how much important is each feature. For example, on the image on the right, you can see that there is a heat map covering the dog, and in this case it means that the network is focusing on the dog in order to return the current prediction. Feature attribution are the most popular kind of explanations supported by visual analytics solutions, and they are used on several data types, and there is an high heterogeneity of visual encodings used to support feature attribution. We can see a couple of examples of how visual analytics solutions can use feature attribution. The first case is the button system, which uses feature attribution to guide the what-if analysis. In this case, it provides to the user a couple of heat maps showing which are the most important and the least important part of the image in order to obtain the current prediction. And the user can occlude some parts of the image, so checking how the model changes its prediction when the input is modified. Another example employed by the Bertini system is to detect and expose the bias encoded in a deep neural network. For example, in this case, the feature attributions and the visual solutions highlight the most important relations among the words in a sentence in a large language models. And in this case, we can easily see that the model is exploiting a gender-specific term connection in order to give the answer, and so it is biased towards the gender. The second category is learned features. In this case, the expansion methods aim to extracting what the neuron learned during the training process. But since there are thousands of neurons inside a deep neural network, the main challenge for visual analytics solutions is to provide a compact visualization of all these informations. So usually what the researchers do is to provide abstraction or clusterings in order to reduce the quantity of informations. A couple of examples are given by the USV systems and the BLUF systems. In the first case, USVs use learned features to visualize what the model learned during the training process, showing the features as a graph connected by edges. And this graph can be used by a professional, for example, an healthcare professional, in order to verify that the knowledge learned by the network is the correct one. In the case of BLEF, instead, they use an abstraction to extract the neurons that change their activations when they are under an adversarial attack and when they are in a normal input, and show what these neurons learned during the training process in order to help users to decipher adversarial attacks. The third category is expansion by examples, where the idea is very simple. In this case, we have our input, in this case a cat, and what the expansion method does is to extract similar examples from the dataset that can be used to explain the current prediction. So the idea is to say, okay, this image is predicted as a cat because the network has seen these similar images during the training process, and they are associated to the class of cats. Expansion methods can be used by visual analytics solution to provide to support several tasks, but in particular here we give two examples for error identification and prediction comparison, used by the melody system and sec-to-sec-this. In this case, the idea is simply showing both the input and the similar samples associated with the prediction and maybe some feature attribution methods in order to let the users compare the different predictions and extract commonalities and differences among them and understand the decision process of the network. A similar category is counterfactual. Also in this case, the explanation methods extract similar samples to the current input, but in this case, the similar sample is predicted in a different class. For example, here you can see an image of 8 that is predicted as a 3 by the network. The counterfactual in this case is an image of 8 predicted in the 8th class. And the idea is that the user can compare the two images and understand which is the missing part of the first image that caused the network to return the wrong prediction. Counterfactual are supported by some visual analytics solution in literature. For example, for doing hypothesis verification, where the user can insert, for example, an input and a range of values for each feature, and the system will show how the prediction change when the values range from a given range to another, like done in the DC system. Another interesting approach is provided by Recast, which use counterfactuals to propose editing in a text systems that aims to lower the toxicity score of a text. In this case, the counterfactual suggests an alternative word that can be used in place of another to lower the toxicity score. The last category is model behavior. This is specific for visual analytics solution, and the idea is to combine pattern mining and some approaches of the previous categories in order to approximate the model behavior and extract policy. A couple of examples also in this case. We have GNN lens, which basically use a linked views of several statistics features and prediction in order to easy the error analysis and identification for the user. Another interesting case is given by CNN2D3, which visualize the logical process by showing a decision tree where each level of the tree compact the learned features of the previous techniques and pattern mining in order to approximate the decision process of the network.
We analyzed the paper according to two main aspects: a core analysis that includes the deep learning domain and the application domain, the target users and the visual analytics process implementation, and a meta-analysis that includes reproducibility and availability, the evaluation and temporal trends. Concerning the domain, we have two aspects to consider: deep learning domain, that is the deep learning research area, for example computer vision, reinforcement learning, and so on, and the application domain, that is, the real-world application like games, medical areas, and so on. Looking to the intersection of these two aspects, we notice that most of the solutions have an agnostic application domain, while on the deep learning domain the most common is computer vision, followed by natural language processing. Concerning the target users, we use the categorization defined by Strobel et al., in which they identify three types of users. Architects, that are deep learning experts and develop or modify deep learning components and architecture. Trainers, that have a background in deep learning, but they only apply existing components to new application domains, limiting the modification only on hyperparameters or data. And users that have a limited or no knowledge at all of deep learning, and they use pre-trained models applying them on their application domain. This categorization is not exclusive, and a system can be developed for more than one category. In that case, we assign the lower expertise category user to the system. This is the detail about the target users and explanation category supported. First, we notice that most of the solutions are for architects and trainers. Feature attribution, explanation by example, and counterfactual are supporting all the three types of users, while the most common are the trainers. Learner feature and model behavior instead require the expertise of users in deep learning, so they are oriented to architects and trainers, but not to end users. Let's now talk about the visual analytics process implementation. We analyzed the solution and present the results looking at the three main visual analytics aspects: visualization, analytics, and interaction. First, an overview of the visualization usage. Almost all the systems implemented a custom visualization along with common visualization paradigms. The most common used visualization paradigms are heatmaps, that are used in general for representing feature attribution or learner feature when the deep learning model works on images, for example. Then we found modeling diagrams that are mostly used to represent the deep learning network. Concerning feature attribution exploration category, the visualization support is highly dependent on the supported data types, but most of the solutions use standard visualization techniques. When the data type is text, the most common goal is to represent the attention-based mechanism, and this is done by using modeling diagrams, Sankey, or word sequences. When the data type are images, the common approach is to use heatmaps or to overimpose feature attribution information on the images. Concerning learner features, it is common for the solution to present novel or enhanced visualization based on Sankey diagrams or NotLink, used for representing the network and the neurons. It is also frequent to use dimensionality reduction techniques to represent the input data or the neurons. Most of the solutions performing explanation by example use standard visualization, mostly heatmaps and NotLink diagrams. The custom visualization are oriented in general to provide details on the text, with enhanced word sequence visualization. No solution use dimensionality reduction techniques. Solutions for counterfactuals have the common goal of visualizing input and output data. There is a wide usage of standard visualizations, and only few use custom visualization explicitly designed for counterfactual analysis. Systems supporting the model behavior explanation category have the common goal of visualizing the model internals. Common entry points of the analysis are NotLink diagrams or scatterplots. These systems show environment of high complexity, composed of several visualizations. A possible reason is that they are oriented to expert users, such as architects. Concerning the analytics aspect, we group complex analytics used in the system in 12 families. The similarity analysis, and the feature influence families are the most prominent ones. Concerning the usage of analytics in the various explanation categories, for feature attribution we notice that the feature influence is the most prominent analytic family. The goal is to identify the most influencing features, and for text data types, for example, is to identify the most influencing tokens in a sentence. For learner features, the prominent analytics family is aggregation summarization. For example, to summarize and reveal crucial neural associations and substructures that contribute to the outcome of the model. For both explanation by example and counterfactuals, the most common analytics families are similarity analysis and search and mining. For the model behavior explanation category, we identify similarity analysis as the most prominent approach, and it is interestingly coupled with dimensionality reduction techniques. We followed the classification of German et al. For the interaction types. The taxonomy identifies 3 types of interaction. Passive observation are interactions that do not allow to edit data and model, but only to explore. Interactive input observation are interactions that allow to modify the input data. Interactive model observation are interactions that allow the user to modify the model parameters like hyperparameters, activation weights, and so on. Analyzing the breakdown of the interaction types with respect to the supported explainability categories, we identified that passive observation are supported by all the systems, resulting in their exploratory capabilities. Interactive input observation are oriented more to confirmatory analysis and hypothesis testings that are fundamental tasks for counterfactual analysis. Interactive model observation are mostly dedicated to feature attribution and to support the model's steerability. As a future research direction, we identify the support of interactive model observation and steerability coupled with the other explainability categories and not only feature attribution.
We now proceed with the analysis of a set of meta-information retrieved from the analyzed papers. The first one concerns analysis of reproducibility and availability. Research question is, how available and easy to use are those contributions? We analyzed the papers following these discrete levels. So just the paper is made available, paper plus demo, there can be video or interactive demo, paper plus source code, paper plus demo plus source code, and in this case, even difficulty in re-implementing the solution using the source code. We evidence that 42 out of 67 contributions just provide the paper, making it very difficult to reproduce the results or eventually to understand how the proposal works, in particular for researchers or practitioners coming from other areas like deep learning or Xi. While 25 raise the availability of materials to 2 papers presenting only video demo, 8 presenting only source code, and 15 presenting demo, both video or interactive, and source code. Interestingly, for these latest 2 categories, summing up from 23 papers, we even look at an integration with general frameworks, both on deep learning, Xi, or visual analytics. And we saw that many of them rely on very state-of-the-art general frameworks like PyTorch or TensorFlow for what concerns deep learning, or D3.js and more general web-based technologies for what concerns visualization, making those solutions easily available and easily interpretable by modelers or trainers. At the same time, the whole picture is of more than 2/3 of the work not making available any materials and making very difficult to replicate or choose for a deep learning researcher to use those solutions or integrate those solutions in the deep learning pipeline. We move on also to analyze the evaluation activities conducted in these 67 contributions, where in this case the research question was how does those solutions got evaluated? In order to conduct this analysis, we split the category in 5 main ones. The more fitting one, so the one with the deepest evaluation analysis, are papers that provide a quantitative user study, just 5 of them, that eventually involved participants recruited to interact with the system in dedicated session and analyze quantitatively their results, eventually using statistical means to prove their benefits or their added value in solving the specified tasks. Immediately later, with 16 papers, we have user study with feedback. In this case, there is still a quantitative user study, but only descriptive feedback in a qualitative form is provided at the end of it, making them still quite robust, but without the full quantitative analysis of the first category. Then we have 11 papers that provided a case study with feedback. In this case, the case studies are realistic, real scenario run by participants that use the tool in a controlled environment for a specific task and eventually provided qualitative feedback. Then 24 papers provided instead a case study but without feedback, so depending on the case, run by the authors or run by participants but without explicit feedback. And finally, the majority, 31 papers, presents execution of a user scenario, so a hypothetical situation where the authors, without any participant or experts involved, used the proposed solution and eventually demonstrated or highlighted particular benefits. Then we looked at the temporal trends of those papers, where in this case the research question was how do research evolve over time? And we look at it from 3 different perspectives. The first one was looking at how the support to Xi methods, summarized in the Xi categories presented, evolved over time. In this case, looking at the chart, we see that feature attribution, even with respect to temporal trends, stay as the measure Xi methods supported by those solutions, with interesting rise of model behavior category and in part to counterfactual and explanation by examples. No matter what, the summarized value tend to stay valid even if considered as their evolution during time. Then we look at those data from support of deep learning models trend. In this case, we see that the results are varied during the year, while at the same time, we can see that the support tend to follow the liveness and attractiveness of new models introduced by the deep learning domain. So in this case, we can see a pretty much stable presence of convolutional neural network and or eventually the raising during the last years of support to transformers or generative approaches, while we experience a diminishing number, for example, for recurrent neural network. This regarded the third analysis that we labeled as model gaps, and results are provided here in 2 different flavors. On the left, we have the aggregated gap computed as the difference in time between the first time a model appeared in the deep learning domain and the first time in which a visual analytics paper has been published using that model. We can see as the median of the whole aggregated distribution is quite close to 5 years gaps. While on the right, we have the distribution of those data by models, and clearly given that the models are affected by, let's say, seasonality, so by the time they were introduced, we can see, for example, how big is the distribution for recurrent neural network that are not necessarily the newest of the model and that present the biggest gap expected given the very long time on which those models are available, while this trend tend to narrow the more we get near newest models like generative models or transformers model that eventually show statistically a strong reduction of the gap in time between when they got proposed and when they get received by the VA domain. On the other hand, we still see that on average we have a gap quite near to 2.5 years. That is still a not trivial time in order to get those models coped with in the visual analytics domain. If we go to summarize all the analysis that we saw up to now, both specific analysis and meta-analysis, we are able to identify a set of research gaps very useful in order to conduct further research. The first one is the uneven support for Xi categories. During this talk, we put the light on it, and we experienced a lot of support for feature attribution and learned features, Xi methods, while instead we experienced a lot of support for explanation by examples, counterfactual, and model behavior, of which have started emerging during the latest years. These gaps is interesting, amounting for the remaining 3 categories of less than 1/3 of the paper. And those categories, those Xi methods, should be more supported by visual analytics solutions in the future. We even experienced a low abstraction in visual support, and in particular in visual encodings, where many works are driven essentially by the data types, tending to use classic visual encodings better suited for the specific data types, images, text, and so on, limiting to representing or try to representing the general overview of how the neural network works. On this in particular, we even experienced the usage of very well-known visual encoding for network representation matrices, node-link diagrams or Sankey diagrams in their classic or extended forms, but that at the same time tend to present well-known limitations in the capability to scale to the numbers or to the dimension that those networks nowadays have. So the call here, the gaps here is in getting a higher level of abstraction in visual support of those characteristics, given the fact that we didn't find it so much spread apart of some works in the surveyed papers. Then we have an uneven coverage of application domains. Interestingly, while deep learning is an essentially domain agnostic discipline, and the same is valid to Xi and visual analytics, we experienced by looking at the paper that just 19 out of 67 specifically target an application domain, where eventually just 8 application domains were covered and just half of them with only one work, meaning that while many of those solutions can be eventually adapted to the fullest range of application domain, this capability has not been tested, not has been proven, and eventually very few will try to exploit on top of the general support of visual analytics to explainable deep learning, even potential specificities coming from the application domain. And finally, there is a lack of attention to end users. The vast majority of the solutions strongly support modelers or trainers to various degree, depending on their objectives, while unfortunately the end users is evidencing a lack of support with very few contribution targeted in. Clearly this comes with limitation given the low expertise or potentially low expertise on the general discipline from an end user that eventually could be balanced by its potential well-known or good expertise in the application domain in which the end user is taken, not simply considering the end user as an unsavvy user, but maybe as a user with a very strong application domain knowledge. At the same time, we are even surprised, and this relink to Research Gaps 1, that the fact that the low support for most interpretable categories like explanation by example or counterfactual that somehow are well prepared in order to be understood by an end user given the strong link to the application domain on which those examples, for the good or the bad, are extracted. At the same time, on top of those gaps, we even highlighted more broad and orthogonal research challenges, looking at this picture not anymore just from a paper point of view, but from a community's point of view. So one thing that we highlight is that the evaluation activities should be improved, and not just simply because paper will gain in quality or will gain in provability of its results, but even because this could help in a way to better align those solutions to the way in which the different communities involved evaluate those properties. Okay? Additionally, given the strong quantitative way of evaluating deep learning solutions, more benchmarking activities, this time involving visual analytics solutions, should be called for. This could help providing additional baselines that could or could not consider human in the loop, could or could not provide benefits to classic way of evaluating deep learning approaches, or eventually explainable AI approaches, allowing capability to test in a quantitative form the proposed new visual analytics solution against them and make their benefits more quantifiable and more provable. A second challenge that we experienced is to provide more support on trustability, with very few works focusing on these aspects. One way to increase this trust in the way in which the visual analytics solutions are used and provide trust in the results with respect to how much explainable is a deep learning model or a system built on top of a deep learning model could be used by incorporating semantics or using ad hoc methods. And eventually, the third orthogonal research challenges that we see is the call for more support to guidance. The vast majority of the systems that we surveyed provide good to very good support to the explorative analysis or to the confirmatory analysis, or in general to provide settings in which the user, models, trainers, and less end users can understand things by exploring the models or exploring the model with XI method. At the same time, in most of those cases, how to conduct the analysis is completely on top of the user that essentially has to project his inner knowledge in order to find the best way to extract information from this scenario. Finally, abstracting even more, we even try to observe what is needed in terms of contextual factors in order to habilitate research for those challenges and research gaps. And this has led us to the topic of better bridging and more bridging visual analytics, XI, and deep learning. Some of the people could believe that bridging is already there, but looking at it more deeply, as we did in this survey, we evidence things that could be improved in order to move this connection and make it more strongly. The first one is clearly community awareness, quite straightforward, as we experienced that a set of bridging events exist coming from the different communities. Many of those activities are just at a workshop nature, sometimes well-established workshops, sometimes very new workshops. And while we are happy of the tendency to have more on this, we still see quite as this joint effort. Would be very cool and very good to try to link more those events in order to foster a transfer of knowledge between those technologies and eventually foster adoption of a mutual solution in between communities. Then we have the suggestion to improve collaborations. This will see at a first glance could see already there, because if we look at authors' analysis, we see that 234 authors were involved in the surveyed papers. That's quite a good number. But if we go more deeper in analyzing them, we see that just 2/3 of the authors come from the visual analytics community, so are already inside our community, where on the remaining third, 64 are from the deep learning community, so a strong imbalance. At the same time, even less are from the XI community with just 23 authors. That is quite surprising given the strong emphasis on explainability at the intersection of these three domains. So we see that unfortunately the composition seems not balanced enough in order to provide a kind of integration between communities and the right dissemination of results among them. And so we call for the integration of more XI researchers in this story and more deep learning research. We believe that similar characteristics could be observed if we look at this picture from the other two categories. We even call more to the development of more middleware software or the integration with very broad and very accepted frameworks. In this case, the advantage could be multiple, even because even today we already demonstrated that there is a low number of papers that expose the code or made available the right materials in order to at least be tested or be tried by the researcher from other community. At the same time, it could still be daunting or difficult to re-instrument those solutions, and eventually a researcher could face strong difficulties that make the researchers drop out from using those solutions. Working on a broader set of communicating API or on a broader set of easily reimplementable solutions, eventually even looking at specific grammars in order to fastly replicate those solutions could be a way to foster disseminating visual analytics in the XI and deep learning domain. The same is clearly valid on the other side, and so from deep learning and XI to visual analytics. This eventually could even help, coupled with the need of more benchmarking activities that we already listed, in order to mitigate the contrast between a data-centric controlled loop that is very peculiar for deep learning with respect to a human-centric controlled loop that is very peculiar for visual analytics, making those two approaches getting near on a common ground and make easy to pass between those two archetypes. Finally, we believe that led by the analysis on the gaps that exist between deep learning and visual analytics, all those activities should bring to a better alignment between the areas where visual analytics solutions for newest ideas at the state of the art in deep learning and XI are produced faster. Faster will not mean immediately, but will mean very aligned with respect to the evolution of the state of the art from the originating fields, trying to minimize the 2.5 years median value that we experienced at best with respect to the more modern deep learning models. At the same time, this effort could even prove useful because it will mean that visual analytics solution could be used in a more exploratory way during the born of those models, and so researchers, models, or trainers could find benefits in a moment in which the research is more live and eventually more experiments are needed to exploit dedicated visual analytics solution to ease this task or to provide alternative ways to work, evaluate, develop, and in the end increase the quality and provide novelty for those models. Overall, concluding this talk, we presented the results of our survey at the intersection of visual analytics, explainable AI, and deep learning that in the end landed on 67 core contributions on which we provided strong analysis in order to let emerge the actual state of the art and research gaps and challenges useful in order to conduct further research. In particular, researchers at the intersection of these three communities or in one or more of those communities could find the good starting point from this survey in order to begin work in this area or begin hypothesizing potential mitigation to some of the problems that we evidenced. And the same could be valid more from a practitioner point of view, where practitioner can be from VA, DR, or Psi again, that could try benefits or could obtain benefits in selecting, given our taxonomy and used features, the best solution that could fit their problem in application domain in this case, and eventually contribute to the research community more evidence of additional problem coming from the users. Finally, we close this talk by declaring that clearly this is a live effort, so we are actually working in order to keep updated this picture, this whole picture, encompassing even works came out at the end of 2022 and now in 2023, some of them even in Eurovis 2023, and that eventually the results of those activities can be found even in the Live Explorer, linked at this URL and even present in the paper, that can allow an interactive exploration of the results illustrated during this talk and an initial basis for filtering, refining, and eventually identifying interesting contribution in the area. With this, I thank you for your attention, and we are ready for questions.